Namaste again. We will discuss about strong and weak shock interaction today. So, I acknowledge John D. Anderson's hypersonic and high temperature gas dynamics. So, we know very well that in the last class we had a discussion, right, on the laminar boundary layer, and we had a basic discussion on the hypersonic flow, which is having a two viscous interaction. One is pressure interaction, which is caused by the exceptionally thick boundary layers, right? Which is otherwise called as the viscous interaction in their own terms. And then the shock wave and the boundary layer interaction, which is caused by the impingement of strong shock wave on the boundary layer, right? So now we will discuss about the strong and the weak viscous interaction. So let us consider here, they consider a hypersonic viscous flow over a flat plate, right? So say consider a hypersonic viscous flow over a flat plate, right? So when there is a hypersonic flow and you see there is a high Mach number m infinity, definitely first thing comes to our mind is a formation of shock wave. I mark this shock wave here. So this is a shock wave. And there is a formation of boundary layer. The boundary layer develop like this and it may become constant to the, sorry, this may become, sorry, to the certain extent, right? So this region is affected by the viscous nature and hence it is called the viscous region, and the outside is inviscid region. And we already know that when there is a streamline and when it enters here and the streamline is displaced because of the formation of boundary layer, that we have seen in the last class, right? Now, this is what exactly happens, right? There is a strong interaction region. So we say that there is a strong interaction region here immediately, right, from the nose or from the leading edge, and the weak interaction region is in further downstream. So here we say this is a weak interaction region, and here we say this is a strong interaction region. So let us say this is V infinity, the Mach number or velocity at a very high value, and this is a flat plate experiencing the free stream, experiencing the free stream velocity V infinity. And we categorize this particular area as a strong interaction region. So the strong region, which has the following effect, right? Following physical effect. And we can say that here the delta is the boundary layer thickness, and delta star is the displacement thickness, right? So let us say here we have a delta, and this is delta star, and this is the outer edge of the boundary layer. And here you have an inviscid region, and of course here also it is an inviscid region, and here it is a viscous region. So we can say that the d del star by dx. So let us take this slope d del star by dx is large here, and here the d del star by dx is moderate. So by this way, d del star by dx is large, and we say that it is a strong interaction, and here we say it is moderate, and hence we say that it is a weak interaction. So let us see the property of the strong interaction and the weak interaction. So let us start with the strong interaction, right? So strong interaction. Say point number 1, in the leading edge region, the rate of growth of the boundary layer displacement thickness is large. So we can say that d del star by dx is large, right? So it means that the boundary layer displacement thickness is large. Second point, here the incoming free stream sees an effective body, right? This is an effective body with rapidly growing thickness. You see here you have a flat plate and the boundary layer is here, and you can see there is a rapidly growing thickness, right? So again, the streamlines over here, the inviscid streamlines are deflected upward into the incoming flow. So we can say that the effective body, the effective body having the rapidly growing thickness, right? Right? Is it audible? Somebody can say yes or no.
Yes.
Okay. So having an effective body shape, right? And having a rapidly growing thickness. And also here we can say that the inviscid layers, right? The inviscid streamlines are deflected upwards. The inviscid streamlines are displaced right, and of course the shock wave is developed at the leading edge of the flat plate, right? So we can say that the shock wave is developed here. The shock wave is developed from the leading edge, right? And the inviscid region is strongly affected. Inviscid region is strongly affected. Right? So the inviscid flow is strongly affected by the rapid boundary layer growth. Then So there is a substantial changes in the outer inviscid flow, which gives a feedback to the boundary layer again. So we can also note that the outer inviscid flow, feedback. So outer inviscid flow feedback to the boundary layer, right? Which is affecting the growth and the properties and so on. So this mutual interaction process, when the boundary layer substantially affects the inviscid flow, which in turn substantially affects the boundary layer, is called strong viscous interaction, right? So we say this particular region as the strong viscous interaction region because of this phenomenon, right? This is a strong interaction. Let us discuss about the weak interaction now. This is just opposite to that, right? Say this is the weak interaction region where we can say that the displacement thickness d del star by dx is moderate, right? Let us note it, the weak viscous interaction. So let us say this is a weak interaction. So the first one, we can say that d del star by dx is reasonably small, and the outer inviscid flow is only weakly affected here, right? The outer inviscid flow is weakly affected here. The second point, the outer inviscid flow is weakly affected. Then if it is weakly affected, then we know that the feedback from the inviscid flow, right? The feedback is also negligible, right? So this region of the flow where the feedback effect is ignored, right, is negligible and ignored, then this region is called, this is ignored, and hence this region is called weak interaction, right? Is it fine? Somebody can say whether this is fine, strong interaction and weak interaction. Then we will continue.
Yes.
Yeah. Good. So we know which one is strong interaction and which one is weak interaction from d del star by dx, right? Yeah. Now let us say there is a similarity parameter in all the discussion. We have a non-dimensionalized parameter which can express us, right? So here we say that the similarity parameter that governs the similarity parameter, say, let us say the similarity parameter. So the similarity parameter, right? Similarity parameter that governs the laminar viscous interaction, right? That governs the laminar viscous interactions. That governs the laminar viscous interactions, both strong and the weak interaction, right? So we define that as something called chi bar. This is called chi bar, right? The meaning of chi bar is like we will have a detailed discussion of the chi bar in the next discussion. The chi bar is nothing but the induced pressure increment, right? The induced pressure increment, right? Induced pressure increment. So chi bar is actually expressed as m infinity cube by root of Reynolds number, which is multiplied by root c, right? Where the c is equal to rho w mu w by rho e mu e. You know what is E and what is W. E is at the edge of the boundary layer and W is the wall, right? Now, the chi bar can define whether it is a strong interaction or weak interaction. So as of now, let us note that the chi bar is greater than 3 and the chi bar is less than 3. When the chi bar is greater than 3, we call it a strong interaction. And when it is less than 3, we call it as weak interaction. Right? So in general, if chi bar has large value in the strong interaction region and chi bar has a smaller value in the weak interaction region, right? So here we emphasize the major consequence of viscous interaction, that is the creation of induced pressure change, right? Induced pressure change or induced pressure increment, which is substantial, right? And this induced pressure change is sometimes called as induced pressure increment also, where the actual pressure ratio P by P infinity along the surface of the flat plate lies considerably above the inviscid flow, which is having a value of unity, right? This is what we have. So the P by P infinity, right? So the P by P infinity value when there is no interaction, this is unity. And when there is an interaction, you have an induced pressure change, and this is with the interaction, right? So this is a flow over a flat plate, and we see that there is an induced pressure change which is strongly affected, and this particular location is the strong interaction, and here you have a weak interaction. I stop at this point. Thank you very much.